So I am Jordan and I work under Scott here, and I've been doing kind of a couple different things, but what I'm going to talk about is the first principles investigation looking at trivalent doping of Syria. So if we consider just pure Syria, here there's a schematic of the cubic fluoride structure, and in yellow we have cerium, and in red we have oxygen. And so some of the properties that make Syria attractive are the fact that it has a high refractive index and dielectric constant, has good mechanical properties and relatively good thermal stability. And it is used a lot in the field of catalysis and solid oxide fuel cells. One of the reasons Syria is so interesting is the fact that it's stable in two oxidation states, those being +3 and +4. And this is due to a small energy difference between the those two oxidation states' valence electrons. And because of this, creates oxygen vacancies, which is what drives its ability to be good in the catalytic field. So if we move on to looking at doped Syria, it's been widely studied. And so here is an example where the ionic conductivity was measured of yttrium doped Syria. And one of the things that has been found, not only with yttrium, is that you can reach a maximum conductivity value with the dopants, and here it's at around 0.12 yttrium. And these are attributed to vacancy interactions. Then here, also a yttrium doped study. One of the interesting things is that this is also observed with gadolinium doping, is that you can see local structural changes, which is seen here in this TEM image. And again, this was attributed to the defect, and in this case, they observed short range ordering. And then in another example of doped Syria, there was a computational study where they looked at carbon monoxide oxidation, and they were able to observe that the rate determining step could be determined through a descriptor of the ionic radii of the dopants. So I'm not going to actually talk about my methods because a lot of you would just get bored looking at equations of DFT, but I use DFT, and so I'm going to go into my results. So what I've done is I first considered pure Syria. And so the lattice constant from my calculations was at 5.497 angstrom, which is around the experimental value. And then here I'm showing you what is known as the Mulliken charge. One thing to keep in mind is Syria in this case should be +4 and oxygen -2. And you can see these values are significantly different. But what's important is the fact that we can make comparison of the Mulliken charges when we're looking at doped structures. So first consideration will be for yttrium doped Syria. And here I've written up in programming notation the reaction. And so you'll notice that I've introduced one yttrium dopant on the cerium site and then a single oxygen vacancy. And moving forward, I'm going to refer to this as one line. And so the lattice constant doesn't change significantly, which is expected at such a low dopant concentration. But what we do see is if we look at the Mulliken charge, and I've written here in red what cerium was in the pure CeO2, is that we are seeing changes in the charge state of cerium, particularly in the Syria in the structure that contains the oxygen vacancy. And I guess I forgot to point out here that in the structure, the purple is the yttrium dopant and the black represents where the oxygen vacancy prefers. And I did do a brute force calculation to kind of see how the dopant and vacancy would like to reside. And they ended up, the most favorable formation energy was for them to be bound to each other. So the second defect reaction I considered, which I'll refer to as 2Y, is now the introduction of 2 yttrium on cerium and then the oxygen vacancy. And again, I did a brute force kind of looking at the formation energy for this defect and found that the second yttrium atom preferred to be bound again to the oxygen vacancy site. Again, not much of a change in the lattice constant. And we can see there's slight changes in the Mulliken charge, but overall, the Mulliken charge for cerium doesn't change too much. And so a lot of this work was actually trying to understand the mechanical properties. And so here is just showing the calculations for the elastic constant. And so when we introduce these defects, we have a reduction in symmetry. So ceria and yttrium, because they're cubic, which have the C11, C12, and C33. But when we introduce these defects, we have other elastic constants that are being introduced. And what's really interesting is if you consider C14 and C44, is that we have these negative elastic constant values. And so the question was, what does that mean? And how does this come about? How does the structure lead to these negative elastic constants? So just to take a step back and think about what the elastic constants are, these are the second derivative of our Gibbs free energy. And we know from our free energy that stability means that we need to have concave up behavior, which means the elastic constants need to be greater than 0. So 1y is mechanically unstable. And the hypothesis is that we can understand these free energy stability by looking at the bonding and the electronic structure, which I did through what is known as crystal orbital Hamiltonian population analysis, or COHP. What's nice about COHP is that we can get bonding information, such as determination of anti-bonding and bonding states. And you can also look at the nature and strength of the bonds between the atoms. One thing is it's not going to give you directly that it's an ionic, covalent, or metallic bond, but it can give you kind of the nature of the covalent bond strength. And so how it does this is it gives, if we look at our density of states, here's an example for the H2 atom where we have our occupied and unoccupied states. And then when we project this to the COHP, we can see that we have our bonding orbitals and anti-bonding orbitals. So applying this to the pure ceria and pure yttria and the two defect reactions I showed you, I'm not going to really walk through all this for time, but what's really interesting is if we zoom in on the 1y, we can see that there are anti-bonding states at the Fermi level. And so the thought is that these anti-bonding states are what are going to determine our mechanical stability. And so to test that hypothesis out, I took the 1y structure, and here I have the COHP for that. Then I did another calculation where I removed an electron from the 1y, and then a second one where I moved 2 electrons from it. And here the COHP, and if we zoom in on the Fermi level, we can see that as we remove electrons, the occupation of the anti-bonding states at the Fermi level disappears. And further, through the mechanical calculation through the elastic constants, you can see that these elastic constants become positive and therefore the material becomes stable. So just as a summary of yttrium dopes, low dopant concentration, as we expect, has negligible impact upon the serious lattice parameter. And we saw in the 1y reaction that we can see local changes in the cerium oxidation state. And then we were able to prove that the 1y defect complex was what caused the mechanical instability in 1y, was driven by the population of the anti-bonding states at the Fermi level. So this was a lot of my work in the past year, and moving forward, I've also started looking at europium doped ceria. And I just have a quick slide on that, and looking at the first reaction. So this is where we have a single europium on cerium, and then an oxygen vacancy site. The europium is in blue, and again, the oxygen vacancy is in black. And there's negligible impact on the lattice parameter. But what's interesting when we compare this defect reaction to the corresponding one with the yttrium is that the dopant and vacancy prefer to be situated differently. If you remember in the 1Y, the oxygen vacancy wanted to be bound to the dopant site, and in this case, the oxygen vacancy prefers to be a second nearest neighbor. And so it's something still investigating, maybe if there's a little bit more scientific reason behind it. The literature usually just is attributing it to the ionic radii. And so I'm moving forward doing a similar analysis for europium in this group here. That's it.
Thank you very much. Questions for our speaker?
Question, more like a comment, and I don't know if this is necessarily related to what you see in negative CeO2 constant, but if you look at Barr stability criteria, that also kind of suggests the same thing. So as you have, and for less symmetric materials, as your C1 goes from positive to negative, then you have crystal concentration state, unstable. You know, your is the same thing, but how connected to that?
Yep. Good idea.
We were planning network oxygen correlation analysis locally around the oxygen society and seeing changes.
I didn't do it, but like visualizing the structure itself, don't really see much of a change as far as that goes. I know as Nate did that. Will you be showing that?
Yes.
Okay.
So, we've been working on some other things in parallel where we put rare earth oxides in the radium oxide. And have seen that the size of the lanthanide makes a tremendous difference in how it oxidizes. And europium being kind of in the middle, I would think that this one would have a strange effect. I mean, with the Syria matrix, you don't have 5+ cation,
Yeah.
but one of the things that we see is that sometimes that local coordination, like Shomik mentioned, you get these BI domains in these fibers and materials, which have local order but long range disorder. So I'm just wondering if you add more europium atoms to this, if you're gonna start seeing something different happening.
Yeah, the issue with that with DFT is more of a computational cost than the size of your system. It becomes really expensive if we go too much larger. But I have seen studies that combine ND with Monte Carlo, kinetic Monte Carlo. And so something I'm interested in, but
I mean, in terms of, you mentioned what the real,
yeah.
why would we care? I would think things like oxidation behavior would depend on whether you had a full solid solution or whether you had clustering, and those kinds of things are important for metallics.
Do you think that the fact that we're seeing the separation between the vacancy and the cation or the substitutional cation could be indicative of this being metastable, and as we add the europium rather stabilizing, that would be.
I mean, you could do this exact model, but as a function of the lanthanide size, and see if you have a difference in behavior and that.
We thought about that because it's curious just that there's a separation, if it's being strain driven or if there's, we don't know what's causing this now.
The work that's ongoing suggests there's a thermodynamic reason for this to happen, because of the Gibbs free energy being lower for the Gibbs PI phase than for the chloride phase.
But is it being driven by the strain, or is it being driven by? I'm just thinking about what if we start turning on and off physics and models, where would we see it start? That's,
I don't know that, just the enthalpy of formation of discrete energy is lower for example, for gadolinium oxide than it is for uranium oxide. So it's much happier in a local environment, it looks more like whiskey like. So you get almost a phase separation of sub-nano scale phase separation that you can observe with that sauce.
Whether equilibrium conditions or strains, light strains or just.
No, these are just equilibrium conditions, these are experimental methods. But this one is also interesting because you're rotating from 2+, so I can imagine this particular case would be interesting, having more different kinds of topics.
and if it's a strain effect, this is something that we could do this changing pressure.
Yeah.
And then look at the energy information as a function of pressure and position. And that would give us some insight into what's driving this
Yeah.
change, and if that then corresponds to what's happening experimentally.
Can you artificially change this to your T+? See what happens.
I know,
We can,
Yes,
we
but
can
the
subtract
question
charge.
is pseudo potentials too.
We can subtract charge, we don't know where the charge goes, it's gonna be distributed in the cell.
So kind of. We can wave our hands and sort of do it.
Yeah, we'll have to look at that. We'll have to look at that. There are things we can do, but I don't necessarily know that they're gonna be representative of what's true.